what are the topics we'll be covering today. So without any further introduction, I'll let Henry take it away. Thanks, Henry.
All right, thanks. Okay, so the tutorial I'll be giving today is one that I've given a couple times for Princeton Computing, and it's normally a 2-hour tutorial, and I have 4 hours of content for it, and now I have an hour. So I will try to go extremely fast and race through everything, or better yet, I will pick a few things, and there's other content there that you can go see that we will not be getting to. So I did put up a poll, which hopefully you responded to. I hope it was a fairly representative group of, because I'll be using that poll to inform what I'll be showing today. And I'm also basing this a little bit on what I saw at the beginning of the lab workshop on the original poll that was given. All right, so first, in order to find this, if you go to the Indico slide, or the Indico page, there is a link there in the Indico. If you refresh your page, it went up a few hours ago. At least I added it a few hours ago, and maybe it went away.
I'll go ahead and add it in, Henry, and I'll also add the link to Binder. So,
all right, I added a link, and somehow it did not stay.
All right, sorry about that. We'll
Can you post a link in the chat?
I already have posted the link in the chat.
Yeah, I'll do that right now.
So there is a link in the chat, and I can post a link in the Slack as well. Also, the easiest way to get to it, if you just go to iscinumpy.gitlab.io, that's my blog, and it's the CPU option here near the top in my little box at the top. So again, that's iscinumpy.gitlab.io. So I'll just paste this one. Actually, if someone else could paste the link to this CPU class to the Slack, that would be useful. Okay. Once you go to that page here, there's a launch binder button. That's the easiest way to get this running. If you want to run it locally, you can do that as well. I'm just going to go and start the binder up and see if we can take a look at what it will look like. I already have a Jupyter Lab instance running, so sometimes it's a little bit unhappy if I start binder after I start a local one, but let's see if it will work. Okay, and it'll ask you a question when it starts up, and just say yes, build. Okay, and in a few seconds it'll ask you to reload the page. And this is standard Jupyter Lab interface. Okay, so we're going to start. I'm going to very briefly go over intro, and then we're going to go a little bit into the Fractal Accelerate. I'm going to spend very little time there, but many people asked for a Numba introduction, but not that many asked for this particular notebook, which was the Numba introduction. So I have to pick one of the two polls. All right. So very quickly in Notebook 00, I'm just going to point out two things here. One is that Python has been rapidly gaining in popularity. This is from GitHub. GitHub itself was written in JavaScript, and now Python is the second most popular language, only after JavaScript. With a different ranking, you'll see that Python is actually doing quite well. And this is the popularity of programming language. Okay, and then just to skip over some of this, sort of the key point here is that Python itself is an interpreted language. When we say Python, we usually are talking about the thing that you get from python.org. It's called CPython, but it's an interpreted language. It's not particularly fast, especially if you're doing loops, if you're doing things like that, because it's doing a lot every single time. It's interpreted, it's not compiled. So they can be hundreds to thousands of times slower than writing something in a dedicated language that does the compiling for you. And in order to get performance out of this, we have found the best way to do this is to take a hybrid approach where you do the things that are conceptually challenging in Python, and then you do the things that need performance with some tricks, either compiling it And I have a mini course over compiled code in Python, which I recommend you check out. The link is right here. Or using a GPU, I have a course over it as well. Or by using the tricks that I'll be showing you today on the CPU without doing a full compile. Okay. And so this is sort of where we'll start. So hopefully you should be at least at this level. You should be able to do basic NumPy, but I think from the polls that I gave, everyone should be pretty comfortable with this. But if not, read over this. This is sort of where you should be coming into this tutorial. Okay, basic. Hopefully you have some basic NumPy knowledge. All right, so let's start. I'm just going to go over the Mandelbrot fractal problem briefly. And the reason we'll do this is because it has an introduction to NumPy. All right, so this is a notebook talk, which you've already been seeing quite a bit of. One thing I really like doing for these sorts of talks is running this line here, which will make it a little bit easier for us to see what's happening without having to be quite so repetitive in typing. Okay, so if you're following along, please just start running these cells. So first I'm just going to import some libraries. We'll talk about specifically NumPy, but we'll talk about these libraries. All right, so the Mandelbrot fractal is a fairly simple problem, but it has some interesting aspects to it. It's not a purely vectorized problem. So this is what it looks like. You take some value in a complex plane, you square it, you add some, and you take some value in a complex plane. You then take your previous result, square it, and add it to that. And then that's sort of the next result. And then you just keep doing this over and over. You start with, you basically just start with 0, but then you just apply this over and over. And the algorithm is just storing where you pass some bound. So where this Z value passes some bound. Usually you choose 2. All right, so let's just try this in NumPy. So this is just a quick way to build up this grid of complex numbers. So I'm just creating complex numbers from -1 to -1.5 to 1.5. I'm going to make 300 of those. Using the J in the third argument here just says make 300 of these. And then I'm making real numbers from -2 to 2, and I'm making 400 of those. It's slightly more interesting if we're not square, because that way we'll catch errors a little bit more easily. And this creates a X and a Y, and then I just do a sum to sum those together. So that's what I get here. So if you look at this, this is a 2D array of values, and that's my C here. Okay. Just so that you believe me, I'm just going to plot the real and imaginary parts just to show you that, yes, that one increases that way, one increases that way. Okay. So now let's try doing this. First, just in pure Python, in pure NumPy. Okay, so in order to implement this, it's really relatively easy. We set up a fractal here. It's going to start off with zeros, and then we just make a copy, and then we're just going to go through and keep updating this Z. Okay, and then every time that we diverge, we're just going to fill in the value here for in fractal. Okay, so we compute the equation you saw above. We check the divergence criteria. We then fill in the parts where we diverged with 2 just to keep it from exploding. Otherwise, you'll hit the end, the numbers that you can represent very quickly. So let's just keep that from exploding. And then the fractal will fill in with the iteration number. Okay. So we'll try running that. And that's the sort of the NumPy way to do this. Okay, so the nice thing is that the only thing we iterated over was I, which we have to iterate over. We can't do this algorithm without iterating over I. But we did not write any explicit loops here. Everything happened in a vectorized form, meaning that that these are arrays, 2D arrays, and then we just provide operations on those, and they happen on the entire array at once, which is how NumPy works. So this is very nice, but it has two problems. First, we have to calculate each of these things separately. So I square Z, I create a new temporary array. Then I add C, that creates another temporary array. And this one I actually saved, so I guess it's not temporary. And then again, I have to do that over again. So I'm making memory allocations, I'm wasting some time there. And I'm not fusing these things together. These are separate runs. I have to do this operation, then I have to do this operation, so forth. The other mistake I'm making here is that, and you can sort of get a hint here, I'm having to do this calculation even though things have stopped. They've diverged. So anything out here, anything large, diverges almost immediately. So that gets its final number almost at the very first run, but I'm still rerunning it every single time because I'm doing this an array at a time. So there's both a benefit and a drawback, especially for an algorithm like this. So I'm just going to take what you just saw, put that together into a function so that I can run it through time it a little bit more easily. So this is just a time it cell magic in Jupyter. So if you just stick $% time it in front of any cell, it will run that multiple times and calculate how long it takes. So in this case, it took 60 milliseconds. If you're running this on the binder, it'll probably take a bit longer. Okay. So if we had calculated this in pure Python, if we hadn't used NumPy, and we'll still use NumPy for the arrays, but if we hadn't used it, this is what it would look like. These are the manual loops that NumPy did for you. So these two loops right here, looping over at the basically the X's and the Y's in that matrix. But the nice thing is, this part, you get to stop. As soon as this is more than 2, you just stop. You stop calculating. You only have to keep calculating if it has not diverged. So that's a nice feature of this pure Python version. So if you run that, it'll be significant. Oops, helps if you define it first. If you run that, it'll be slower, but maybe not as significantly slower as if this was a highly optimized NumPy problem. So 10 times slower instead of, often this is 100 times slower when you go to NumPy, when you leave NumPy. But the nice thing is, so we'll just rewrite this one more time. This time we'll break this up and we'll use good software engineering techniques. We will write just the part that runs on each value, the inner part here, as a separate function. And then we'll write the part that applies it here. All right, now I'll rerun that. Should be about the same. Actually, I think sometimes this is slightly faster. But we just broke up the problem, and this is easier to read because now this is simply doing the fractal calculation on a grid cell, and this is applying it to the grid. In fact, this function right here, we could just throw away. We don't even need it because NumPy has its own version of that, an np.vectorize. So np.vectorize will take any function and turn it into a function that works like, that works on, so see, this is actually a function now. This is now a function that works on any array, and it does this thing on each element of the array. So again, we'll time it. So notice again, I didn't use this function at all. I was able to just do this one. Give that just a second. Let me see if there's any questions. All right, someone, if any questions come up that need to be addressed quickly, please just let me know. All right. So this actually, I'm not quite sure why this one. Yes, go ahead.
So it's probably because I'm running on Binder, but actually when you said things should get faster originally, it became slower. I assume that's because more people are trying to use Binder at once and it uses some sort of clock time, not personal execution time. Does that make sense?
Yes, it does. And because you're on shared resources with Binder, your performance numbers can vary a lot there.
Thank you.
The order of magnitude should be correct, but you definitely may see some differences. Okay. Very good. All right. So and then I'm just going to plot this again just to make sure we did the same thing. But this is doing it may be doing some small optimizations, but it's still basically a Python. You're still running Python here. Let me just show you a trick. Whenever you talk about performance, one of the most important things to talk about is profiling. You do not want to optimize code before profiling it, because optimizing code usually makes it uglier. Some of the things I'll show you may not, but often it does. So you want to make sure you're actually optimizing the parts that are slow, that are slowing down your problem. So there's actually a really nice line profiler package, and it has nice IPython support. So I'm just going to load the line profiler package. And then it has a new magic called LP run. And so with LP run, it's a magic, so you put a % in the front, LP run. And then you give it a function, -f function you want it to run. So fractal numpy is the function we want to profile. And then you just tell it some code to run. In my case, these are the same, but maybe this is a function that's inside that function. That's fine. Okay. So if I run that, it will profile that function line by line. So now I see how much time this took on each line, how much time it took each time this line ran, how many times the line ran, and what percentage of the total time this was eating up. So you'll see that this divergence calculation is quite slow, and doing this array calculation is slow. The masking part is a bit faster. And certainly the memory allocations are pretty quick. The ones not side loops. Okay, so that would, if you were trying to optimize this, you now know what lines to target. It doesn't make sense to try to optimize this line before you optimize this one, because half your time is spent in this line. Now, if you don't happen to have line profile, if you're using Conda, it's pretty easy to get. But if you don't happen to have good access to it, there is something built into the Python standard library called cprofile. And unlike most of the modules that had this name, this one is still around in Python 3. They merged most of the other modules, but this one, cprofile and profile, are different. So they were not able to merge those. So it's actually called cprofile with a capital P. And if you do that, this runs. However, this runs function. This doesn't run line by line. This just times function calls. So it's a bit harder to read the output of this. But it's another tool for your tool belt. You might be able to get a different set of information out of this. Okay. All right, so let's take a very quick look at numXpr. numXpr was, it's actually pretty hard to use numXpr for the problem there. You can, but it's a bit tricky. But let me just show you what that would be used, how that would be used. So numXpr will take a calculation, and then it just in time compiles that calculation for you. So I give it a string here. So I just basically copy and paste this. I'm going to go ahead and do that so you can tell it's exactly the same, and run it. So it will do a just-in-time compile, and now you're running actual machine instructions that fuse these together. But you'll see for something like this, which, or a comment here, but I'm pretty sure this is literally one of the examples in the numXpr documentation. You'll see you don't get much out of such a simple thing. And that's mostly because I think this is mostly because NumPy is now actually fusing simple operations. So it's pretty much doing what numExpr is doing for very simple operations. Let's try an operation that's not so simple. Let's copy that in. Let me just block that. Oh, I don't have that. All right, so that takes 2 milliseconds. And now if I do the same thing, here, you'll see that that is a much more significant speed up over pure NumPy. Again, this is speed up over pure NumPy, not over Python. So this is really nice, but you have to know where it's useful, and NumPy can't automatically be doing these fused operations to begin with. But if that's the case, you can actually get a nice speed up. This actually runs, this does the just-in-time compile very fast. It caches it, but it's very limited. The stuff you can put in this string is a very limited set. So the next thing to see is Numba. So Numba is actually a full just-in-time compiler. It can take, and so what it does is it takes the Python bytecode that you get whenever you create a function, and then let me actually show it to you this way first. So I define a function. Actually, for in the interest of time, so you can inspect that function and take a look at what's inside. I'm actually going to not do that in the interest of time. I do have less time than I usually teach this. All right, so let's just take a look at the Numba vectorize. So it takes this function, it then analyzes what's inside, and then it converts it to LLVM code and compiles it through the LLVM engine. So it does just-in-time compilation. So the very first time you run this, it is significantly slower because it's actually compiling it. So let me actually I can at least show you that. Okay, so I'm just going to do time. So I'm going to reevaluate the function definition. I'm going to run it the very first time. You'll see it takes about 43 milliseconds. And then I'm going to run it many times. And you'll see it took 44 microseconds. Okay, so this is the initial just-in-time compilation step. And this is the actual time it takes to evaluate each time. Okay. So this is actually very, very nice. So what we're going to do is we're going to go take our original function up here. There we go. Yeah. Let's scroll back up, and we're going to look at that this NumPy vectorize, and we're going to replace this with Numba. Okay. Now we're going to run this. The timeit is going to be a little bit unhappy because it takes significantly longer to run. Actually, it wasn't all that unhappy. And now you'll see that we're running this in about 400 microseconds. So this is now quite snappy, except I've changed that. Okay. All right. I think I changed one of these things later on. Okay, so let's just do a demo. If you're doing this in your in Binder, I think my Binder instance is dead. Yep. Okay, I let that time out. So if you're doing this in Binder, what you're going to want to do, it uses two things. It uses a Jupyter Matplotlib extension for JupyterLab, and it uses a Jupyter widgets extension. The matplotlib one should have tried to build when you first started. And if you click on the extensions tab down here, the extension manager, you'll see the list of your extensions. Make sure you have Jupyter widgets installed. You can just copy and paste that in and put it in the search here. And if you've not installed that before, you can just click install. So if it like this one, I can just click install. So you should have Jupyter Matplotlib and Jupyter widgets installed. So those should be listed here. Okay, it'll ask you to rebuild and just say yes. And that's actually rebuilding the JavaScript. Okay. So let's try this out. So I'm just redoing the same thing we did. So this is a just doing a just-in-time compile of that. And now I'm going to run this function at the bottom. So this is what we just saw. This is just adding a widget around it, an interact widget. So there we have a fractal. And if you take this and, for example, you adjust the scale, these are being recalculated live. And then if you just go back up and change this to fractal number, and then you can take that same thing, adjust it, and you can see the difference. Now it's nice. It's much, much, much smoother just scrolling in and out of that. So it sort of changes by changing how quickly you do things. You can actually sort of target different applications.
Henry, what sort of machine are you running on? And do you have a GPU backend or anything like that?
This is just running on a local MacBook. It's a CPU backend and it's a single core.
And if you had a multi-core machine, or if you want to use it, or if you want to use a GPU, does that happen automatically?
Not automatically, but it's very easy to add. I'm not completely sure why I did the ingit version of this instead of doing the, oh no, that's right, that's the one that you want to do. So you can do parallel fours, parallel ranges. And you can also do, you can target different things here. There's also a CUDA jet and a, there's one for ARM, for AMD as well. So you often have to think a little bit differently. You have to be a little bit careful with how you write it, especially when you go to GPUs. You often have to restructure this a little bit, but you can use it. For parallel, I may have another example where parallel is turned on. You can take advantage of that almost automatically.
Henry, you have a request in the chat on Zoom. Maybe if you could just repeat the widgets step to install it.
Ah, yes. So yes, this is a few steps install. I'm not very happy with the way that Jupyter Lab extensions install. They're trying to be safe, but it's kind of a pain. So you have to have the extension manager. This is how you install them from inside from this. I can pull up the chat to see what the problem was. Okay, so so I'll just repeat the instructions there. So you just click on the extension tab, which is this little thing that looks like a puzzle piece down here. And that will list all of your extensions. You can see that I've installed 3 extensions. The Conda Forge package for Jupyter Matplotlib actually installs this extension for you. It just has to build the JavaScript when you start. The Conda Forge package for this one doesn't install the extension for you, unfortunately. I think that's probably an issue with that, with their package. But you can just copy and paste some portion of this name, put it in search, and then it should list. I've already installed it, so it's listed up here instead of down here, but it should be listed under your search results. Then you just click install. Okay, so, and then it will ask you to rebuild. And there'll be a little blue tab across the top. Is there another? These are the 3 extensions I use most of the time. think that's the one I used, maybe not. There we go. So I added a spell checker. And then see it says a build is needed to include the latest changes. So if you click that, it will rebuild the JavaScript for Jupyter Lab, and the page will reload. So that's exactly what will happen for you when you're installing the widgets. I was able to run it on Binder earlier. It's just hard to keep the Binder, since I'm running this locally, it's hard to keep the Binder alive.
Have you seen the activity on the Zoom chat? There's people have. Is that what you're talking about right now?
Yep.
Okay, gotcha.
And then some of these, when you open them, may ask you for a kernel. Obviously, you're not going to have my list because you're running there. I think both of them may work because there's really only one Python, but yeah, the one that was listed there, the Conda Env notebook, is the correct kernel to select. It will be the default, I believe, when it asks. Okay. So let's go to the Markov chain Monte Carlo sampler example, and then we'll do distributed. We will probably not have time to talk about low-level callables, even though those are really cool. All right, so this is another example for Numba, and this is taking a sort of the first step in building a Markov chain Monte Carlo generator, what's called a Metropolis sampler. Actually, I guess I'd implement the first one and then I implement. All right, we'll go through the sampler in detail. So this is, we're going to start with sort of the obvious way to implement this. So this is how I initially implemented it. I went through, I needed to do some, I needed to get a normal distribution, so I found one in scipy.stats. Seemed like a fairly a natural thing to do. And it provided a fairly reasonable interface, so I used it. So this is what this looked like. This is just following the algorithm, which is you basically make a proposal based on your current guesses for a statistical distribution. You then calculate likelihoods and priors, and then you decide whether you want to accept that proposal or not. And if you accept, you update your current estimation for a parameter, and then continue. So that's just a basic sampler algorithm. The focus is really not on the algorithm itself, but how we can optimize it. Okay, so if we run this algorithm, we give 15,000 samples. The binder probably will be a little bit slower. While this is running, I can answer one more question in the chat. Yes, that's the Jupyter page will reload itself when it's finished building. So you just have to wait a little bit and then the page will reload. This is definitely supposed to be slow, but this is even slower than I remember it taking. I think what I was supposed to do was start this and then talk about the algorithm. I think I did that in the opposite order. Oh well, no, there we go. So this took 46 seconds to calculate. That's really, it's fairly interesting result, because this is, see, these are the points. So the left plot here is just looking at the points as it's hopping around. But if you make a histogram over that, over those samples, and I really need to switch this over to using Boost histogram. I just noticed that. If you look at a histogram over these samples along this direction, it actually creates the distribution. You see, you actually get the distribution that you're wanting, even though this is a random sampling and it's basically just jumping around back and forth. It's generating this distribution. It's really quite fun when you put in, when you do the Metropolis sampler, which is a slightly simpler version of this. You can actually generate interesting distributions from it. It's a fun thing to play with. So obviously, I made a performance mistake. I really didn't expect this to do 15,000 points to take almost a minute. So let's take a look with LP run. Since I showed you earlier this LP run. And if you do LP run, you probably want to run a much shorter piece. So I'm running 1/10 of a 1/10 the amount of data. Okay, and now you should see, minus the poor line wrapping because I forgot to close that. Now you should see where all the time is being used. It's these things. We are spending a tremendous amount of time doing the sampling with these SciPy stats. Now, it turns out the SciPy stats were designed to take large arrays. They were not designed to do smaller calculations like this. They were not designed to do one value as part of some sort of looping algorithm. They were designed to be instantiated once, so this part should happen one time, and then this thing where you hand in data, this data should be quite large. Okay. So if we just simply recompute this or re-implement this norm, so that's really all it takes to implement this norm of a Gaussian. And then if we compare those, always test, always compare. So you can just do a quick assert between those and verify you're actually getting the same thing back out. So now we're going to try this again. And I made one other change which doesn't make as large of a difference, but I also got rid of the list appending because appending to a list is slow and bad. Just a second. I don't actually have the, so someone asked in the chat if we could do a go faster, go slower. And I don't think that's enabled for this room, or at least I don't see it.
Oh yeah, I was just wondering if you can somehow gauge
that's a good
the room.
suggestion, and I've used that before, but it does seem to be turned off.
Maybe for you, but not for other people.
For people who aren't, they can use it.
I am both. I'm connected with my iPad.
It is there, Henry.
I can use it. For example, if you look at mine, I can say faster and slower, right?
Yeah, people are clicking
But
randomly.
it doesn't tell me that you, so I should have a little list that tells me what people are asking.
Well, it's 3 go fast. It's been jumping up and down. One
Ah,
person
no, I
said
found it.
yes.
I forgot which, it's my fault. I forgot which window it's in. It's in participants, not the chat. And it doesn't show up on the iPad, unfortunately, in participants.
But actually, if you want feedback right now on how this is going, so the 70 people in the room, should he go faster or slower? Press the button. You'll find it under participants.
Faster or slower? Click on participants, not chat. Click on participants. And is this a good speed? Do you want to go faster or do you want to go slower?
And while you're figuring that out, just remember that everything's recorded, so you'll be able to watch it later at whatever pace you want to go.
Just going to go ahead and run the next one while this vote is going on. All right, generally go faster.
Faster, yeah.
Few people want slower, and 5 people.
10% of you say go faster.
Thumbs up would be if you like the pace.
Yeah, there's 5, 6 of them.
I forgot about thumbs up. Oh, okay.
10 of them.
I think the pace is actually, keep the pace the same is winning.
Yeah, right.
Okay, maybe a hair faster. I keep the pace. We still have more to go through, and I think people want to see the other parts. And yeah, you can rewatch it if I do go a little too fast.
Yeah, since the tutorial is an hour, maybe we can take another 10 minutes or so to go through material, and then we can take the last 10 minutes to focus just on questions people might have.
Okay. So the 2 changes, I got rid of the list appending, which wasn't really a very large part of this. If you look at the list append portion, is actually not that much of the time comparatively. It's definitely, it sticks out, but it's nothing like this. And I just did my own NumPy version, the same thing. This is 15,000 samples. Took half a second instead of a minute. Okay, so we did really well so far, but let's go further. We can easily do more than that. You shouldn't stop there. So I can just take that same norm PDF that I calculated. Now I can just calculate it in pure Python. I don't need any of the I don't have to do the NumPy things. I could use math.exp here if I wanted. And then use the vectorized decorator. The vectorized decorator in Numba is really nice if you have something that applies identically to a set of points. So with the vectorized decorator, notice these are not arrays. These are just float, 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 float. However, if I pass in an array here, I get an array out. Okay, so it does that vectorized for me. Okay, and so just doing that, I already made a noticeable improvement, but the function is still spending a lot of time in those other portions. So if we take a look at the profiler again, our likelihoods are actually spending more time probably in the prod than the norm, because you'll notice the this norm PDF probably should have been up here too. This is probably where you're spending your time. You could also look with the function profiler and see how long function calls are taking. Well, now we can take, we'll just take this norm PDF once again. We'll this time do an injet because we're going to use it inside another injet function. So we don't really care if it's vectorized. We just want it to work on a single value, because now we're going to write a function where we do single values. And then we're going to put injet around the entire sampler. Now, in order to do this, now that I got rid of the SciPy parts, it pretty much is the same function. I didn't really have to change anything to do the injet version. Okay. Okay, well, the first time that took a second. Oh, that seems even worse. But wait, let's try that again. And you'll see now it takes 20 milliseconds. So we started off with something that took a minute, and we're now down to 20 milliseconds. I'll leave the Metropolis sampler to you because I really want to do a little bit of the distributed section, but this is a much simpler algorithm. It's really fun because you can put any function you want in, and then you can use this sampler and then do a histogram over it, and you'll see the distribution coming out, which is really, it's quite fun. Once you get through the, I think this also has a burn-in period, if I remember. Yeah, so you have to, so you want to look at, once it finds its equilibrium, you can then just generate values in that distribution. It's a lot of fun to play with. It's a relatively short algorithm. You can read through it there. And with Numba, it can be quite fast. Okay, so let's take a look at multiprocessing. So in Python, there's two types of multiprocessing. You have multi-threading, which is where you run one Python process, and multiprocessing, which is where you have multiple Python processes talking to each other. Okay. So multi-threading is not as powerful in Python as it is in other languages like C++, because you have only one Python instance, and Python memory can't be changed. And almost everything you do in Python, at least touches the Python memory, without making a lock on the global interpreter. So it's called this global interpreter lock. Sorry, I like double clicking, and Jupyter doesn't like me double clicking. So you have this global interpreter lock. Now, this only affects Python memory. That does not mean you can't run two things at once in Python. It just means that if they are running Python code, they are switching back and forth with the Python scheduler is just running one command and then another command. It's not using your cores. If, however, you are running things that do not use or that are not written in pure Python, for example, NumPy or things like that, that internal code, as long as it tells Python that it is not touching the segments where it's not touching the Python memory model, those segments are not included in the rule I just said, where you can only run one thing at a time. So Python will start up something, it will release the global interpreter lock, it will move over, it will do something else, and then it will come back later. So you can actually get multiple things running at the same time on multiple cores through Python with threading, but it has to be running something that releases the global interpreter lock, which means it has to be running something that is not Python. Okay, but that includes the compiled internals of NumPy. NumPy has actually been getting very good at doing this in recent years. And if you're using boost histogram, for example, that's very careful to release the global interpreter lock. A well-designed library should do that. Okay, so let's take a look at an example. I'm just going to take a piece of the fractal example. This is one of the reasons that I wanted to do that example at the beginning. And I'm going to first run it on a very large problem. This is a 4,000 by 3,000 problem, so it takes about 3 seconds. And I'll just prove to you that that is, in fact, a fractal. Okay, so now I'm going to take the same problem, and I'm going to try several different methods of computing it on multiple cores. The first one I'm going to try with multiple cores is with raw threading. And so I'm just creating getting very close to time. I'm creating a thread. I'm telling it what function to run. So this is my function. And then each time it runs, I'm giving it a new set of arguments. So arguments is just a tuple, and they are the arguments to this function. So they're this. Okay, so this just evaluates this in pieces. Because I'm just passing it slices, I don't even need to worry about transferring memory around. It's actually just getting views of the original memory. Okay. If you are curious, this would be the object-oriented interface to do that instead. Okay, and you can see that our wall time is now down to 1 second, when before it was 3 seconds. So NumPy was actually, so this was actually running faster than when we first did this. How many threads did I do? Check. Oh, I did way too many threads. Okay, so I split it up into 400 threads, which is probably not an ideal. You'd probably want to use slightly less than that. Okay. But if we do this again, you'll see you get the same result. So a much higher level interface to that would be executors. With the executors, you have both a thread pool executor and you have a process pool executor. So you can actually switch to the processing model quite easily. The nice thing about the executors is they do the management of the chunks of work for you. So here I say that I want a maximum of 8 workers because I have an 8-core machine. Okay, so now I'm going to do the same piecing. And then to register that, I'm just going to give these to executor.map. Okay? And then for each item in here, I just simply wait for it to be done. So I do nothing. I just say, well, loop over it. Every time one of these is done, it pops out of this loop, and then I don't care, so I just keep going. Okay? So this is happening. They're all running in parallel, and you'll see I've got a little bit faster again. So I have a little bit less overhead now, since I only have generated 8 threads, and then I'm feeding those threads. Oh, massive difference for this. But it can. If I do processes, this would make a very big difference if I did processes, because processes are expensive. This is pool executor. So there I ran it in separate processes. And you'll see that it dropped from, so you'll notice two big changes. One, this number changed a lot, the CPU time. And that's because there are now other Python processes running, and those Python processes are not counted as part of this process, so you don't see that time. But the wall time still dropped from a second to 6/10 of a second. So now this is not having to deal with the global interpreter lock, but it is having to transfer the memory out to these processes, or shared between these processes. All right. Okay, and then you can actually manually share the memory. So this was still transferring things back and forth through pickles, which is not ideal. So you can actually share memory. This is really easy in Python 3.8, but in older versions you can still do this, and it's not that The interface is not that bad, though you do have to use these raw interfaces with raw types. Multiprocessing.shared memory makes this a little bit prettier. Okay, so here I create a shared array. So this is in memory in a place where multiple processes can see it. And then I'm going to do that process pool executor again. And you'll see that that did slightly better. And the output worked. Okay. All right. There is a Dask example that's a little bit harder to set up, at least to do anything interesting. So that's probably a good spot to stop for questions, and then maybe if somebody wants to see it, we can run this piece too. But let's go ahead and stop there and take some questions.
Okay, thanks very much, Henry. This was great. Obviously, a lot of engagement on this one. So let's go to the Q&A. Here, I'll also go ahead and post the present mode view of that, if you can click on that on your machine.
If I can click where?
And if you go to the Zoom group chat, I also posted the present mode so that it's a little bit easier just to have the questions up for viewing on the video later.
Okay, and just to point out, somebody mentioned this loop is in order, but there is a way to go out of order if you want to grab the one that completed first. But the overall timing is the same. That when they're all done, this will be done too. Okay.
So people first just want to know if there's a video of you going through your whole course, or if that's something that they should be on the lookout for in the future.
At some point, I would like to do this more slowly and do a full recording. I actually do have a recording from when I did it once. I don't remember if it was this session or if it was the compiled Python tutorial. And there is a recording of that, but it's, as far as I know, it's not public, and I don't know who. I don't know if it's ever. I don't know even where it is really. I do know that Princeton was recording it.
Okay. Yeah. Well,
but I would like to record this at some point. There's several other things in there.
Was that CODIS-HEP? Do you remember? That wasn't CODIS-HEP?
No, it was one of the Pixie tutorials.
Oh.
Would have been recorded probably if we had done an online CODIS-HEP this year.
Well, maybe we can try and set that up through IRIS-HEP in the near future.
I think that would be a great idea.
Okay, and then let's see. Moving on, we have a question from Ben about NP vectorize. So I always understood NumPy vectorize would be the same speed as the equivalent set of Python for loops, and it was purely for convenience. But the result for the Mandelbrot set was noticeably quicker. So what is
that?
What?
That is something I also assumed too, because it is written in. I mean, it's definitely not doing sort of the NumPy things. I'm not totally sure why it's faster. I've dug into the source code a bit. It may be that it's doing the actual looping in C and then just doing a callback to the Python, but the actual loop checking and things are in C. But it is noticeably faster, and I've always noticed exactly that. In most cases, though, when you're doing more computation, it's not as noticeable as that. That was a relatively simple example. But in larger circumstances, it's usually not much faster. But it's usually at least as fast, though, as writing your own loop. So if you're going to write a loop like that, go ahead and use NP vectorize. Yes.
Okay.
If anybody finds out more about why NPI, if they can have a better explanation for why NP vectorize is faster than writing your own double Python for loop. It definitely won't be doing a double loop. It does a single loop through, which possibly could be part of it. Okay.
Yeah, so Paul wants to know, can you
So
comment
in
on
Numba, what
using
about no Python? And so what I was actually usually doing was doing ingit, which just puts the no Python equals true for you. So no Python forces it to compile, whereas without no Python, it used to, and maybe still does, have a fallback mode. It'll usually print a warning, but it'll fall back. And fallback mode usually doesn't do much of anything other than it can sometimes compile bits and pieces, but it's really still running Python, which doesn't give you the speed up you want. So if you're using Numba, you should almost always use either ingit or no Python to do that. Jim, do you know if they've changed that in one of the most recent couple releases?
Yeah, so they're switching to ngit being the default. That's what's changing. The meanings of yes with Python or no Python are the same.
But the default basically will be no Python.
Yeah, the default is, because the only reason you're using Numba is because you want it to go faster anyway. So if it just goes slower without telling you, that make people unhappy. But it is useful. It is a useful mode because if you just say numba.jit in Python mode, I'm not sure what's called with Python or something else like that.
No Python equals true. Oh, sorry, no Python equals false.
It was false. Okay, yeah.
Right.
So it's a double negative.
Yeah.
So what it does is it searches through to find any inner loops that can be compiled. So it might compile half of your function. And that's pretty useful because then you don't have to search for the parts that can be statically typed and the parts that can't be statically typed. So it has a point, but most people just want the whole function to be statically typed and to deal with the errors. And so that's becoming the default.
That's why everybody's using ingit as well. Just if you're using Numba, the point of using Numba is to use Numba, but yeah, there are some times when that can happen. Yeah.
Okay, and I think we just have one final question. Okay, so can you go into a little bit more detail about Numba versus SciPy as it relates to the example in the MCMC notebook?
Versus is maybe they're not necessarily in competition, but so they're I mean, they're not really comparable in that they don't do the same thing. SciPy is a collection of functions, and I wasn't necessarily making the point that all SciPy functions are slow, but just blindly using them can be a problem. And specifically, the one that I was showing, it had some very nice, it had a nice API for distributions. But I wouldn't say, I think Goofit has a nicer API for distributions, but it has a partial nice API for distributions, so it was easy to find it and use it. But it wasn't designed for what I was using it for. It was not designed to run many times. It was designed to run on to be implemented once. So you'd have some distribution, you would set the parameters, and then you'd create an object, and then you would run a bunch of data through that distribution. Whereas Numba's a compiler, and you're able to do just-in-time compiles, whereas inside SciPy, they don't have just-in-time compiled code. They only have pre-compiled code. But if you look at lesson 7, which I didn't go into, the low-level callables, you'll see a way to take many of the SciPy functions and give them Numba callbacks. So for integration and differentiation and image filters, things like that, you can actually compile your code in Numba using the Numba cfunc, and then hand it that pointer, and it will skip the Python call in the middle, and you can actually have an extremely fast routine where SciPy is doing the heavy-duty handling of doing the integration for you or whatever it is, but you can also you avoid any Python calls in the middle. If you have to look at one thing in the slide, it would be this one. It's slow to do compiled code that calls Python that calls compiled code. It's much better to just have compiled code that calls compiled code there's actually a way to do that in SciPy and NumPy.
Nice. All right. I think that's all the questions we have. So we'll, oh, I guess actually there's 2 more that popped up. So maybe we're already past an hour, but maybe we can take just 1 more.
You can take this 1 more question. So does it automatically support a multi-core? And I skipped that part because I didn't have time to go into it. But I kind of had a question for Mike, I think, on that as well. You can use multi-core. It's not automatic, but it's very easy to use. And you don't always want to use it. It doesn't always make things faster. Let me see if I have one that does the number vectorize. I figure out what the difference in the output is there. But so if the number vectorize, you can I'm getting ingit and vectorize mixed up. But one of them you can set parallel equals true, and then the other one has different targets that you can set. As well. So it's usually something like adding an extra parameter. If it's in the vectorize, it's pretty much that. And then in the ingit, you can get control over it. There is a number, I think it's number dot. There's a number.p range, so that's a parallel range. So you can loop from something else, and this will happen in a parallel loop as well. So you have some control over it, and there are some automatic options. But it takes a little longer to start up the parallel, so if you have a very small piece, number is extremely good. If you have just a tiny little function you want to call many times, number can actually do that very well as well. But you definitely don't want to turn on the parallel for that because it takes time to set up and break down the parallel infrastructure. Yeah, I'll try to update the tutorial to have a mention of that somewhere. I think it may be there in one of the lessons. I'm pretty sure it's there in one of the lessons. And the number docs are quite good, and there's a nice section on parallelization there too.
Okay, well, once again, Henry, thanks very much for this really, really nice tutorial. And we'll go ahead and migrate those questions over to the Slack as well. And with that, that's it for today. So we'll see people back here for day 4 of PyHEP tomorrow.